This video is designed as an introduction showing how to use OptiTrack cameras to set up an LED wall for virtual production. This process is also called In-Camera VFX or In-Cam VFX. As an industry technique, it is used to simulate the background of a film set to make it seem as if the actor is in another location. Section 1. As far as OptiTrack hardware is concerned, you will need all the typical hardware for a motion capture system. This includes things like Ethernet cables, switches, truss, clamps, and of course, OptiTrack cameras. Additionally, you will need an eSync, a CinePuck, a probe, and a few extra markers. You will need two computers, one for motive and another to run Unreal Engine. For the motive computer, the CPU is the most important component and should use the latest generation of processors. For the Unreal Engine computer, both the CPU and GPU are important. However, the GPU in particular needs to be top of the line to render the scene. We are using the RTX 3080 Ti for this example. Setups that involve multiple LED walls stitched together will require graphics cards that can synchronize with each other, such as the NVIDIA A6000. The Unreal Engine computer will also require an SDI input card with both SDI and Genlock support. We used the Blackmagic Decklink SDI 4K and the Blackmagic Decklink 8K Pro in our testing. You will need a studio video camera with SDI out, Timecode in, and Genlock in support. For our testing, we used the Sony PXW FS7, but any studio camera with the BNC ports listed previously will work. Cameras without these synchronization features can be used, but may look like they are stuttering due to frames not perfectly aligning. A camera dolly or other type of mounting system will be needed to move and adjust the camera around your space. You'll also need a variety of cables to connect different devices together, but those will all not be listed here for simplicity. Your studio camera should have a cage around it in order to mount objects to the outside of it. You will need to rigidly mount your CinePuck to the outside. We had used small rig Nodal rail and clamps for the cage and rigid body mounting fixtures. Many systems will want a lens encoder in the mix. However, this is only necessary if you plan on zooming your lens in and out between shots. We do not use this device in this example for simplicity. In order to run your LED wall, you will need two things. First and foremost, you'll need the LED wall, but separate hardware called a video processor is also required to control the images displayed on the LED wall. We had used planar TVF-125 for our video wall, but there are many other options out there depending on your needs. The video processor we used for controlling the LED wall was the ColorLight Z6. However, Brompton Technology video processors are a more typical film standard. For large walls composed of LED wall subsections, you will need an additional video processor and an additional render PC for each wall, as well as an SDI splitter. We are using a single LED wall for simplicity. You will need generators that are able to output both timecode and Genlock data. Timecode is for frame alignment, and Genlock is for frame synchronization. We used Blackmagic Mini Converter Sync Generator for Genlock in combination with the Tentacle Sync for timecode. Any timecode and Genlock generators will work. These are just what we used. The timecode is fed into the eSync 2 and the studio camera, which forwards this information to the SDI card. The Blackmagic Sync Generator sends Genlock to the eSync, to the studio camera, to each SDI cards used, and to any other video devices that need to be frame synchronized. Proper Genlock setup is important to frame align the different systems. A rigid board with a black and white checkerboard on it is needed to calibrate the lens. However, this object will likely be replaced in the future. Section 2. The next topic to cover is how to configure motive for tracking. We assume that you have already set up and calibrated motive before starting this video. If you need help getting started with motive, then please consult our wiki for more information. The first thing that you'll want to do is set up your active hardware. This requires a base station and a CinePuck. Plug the base station into a power over Ethernet switch, just like any other camera. Firmly attach the CinePuck to your studio camera using your small rig Nodal rail and clamps on the cage of the camera. The CinePuck can be mounted anywhere on the camera but for best results, put it closer to the lens. Turn on your CinePuck and let it calibrate the IMU bias by waiting until the flashing red and orange lights turn into flashing green lights. Optionally, power the CinePuck using a USB connection so that it never runs out of batteries. A light should turn on when the power is connected. After this is all done, switch to Motive. Change the tracking mode to passive plus active. Create a rigid body out of the CinePuck markers. For active markers, turning up the residual will usually improve tracking. Go through a refinement process in the builder pane to get the highest quality rigid body. Show advanced settings for that rigid body, then input the active tag ID and active RF channel. If you don't have this information, then consult the IMU tag instructions found on the OptiTrack wiki. If you input the IMU properties incorrectly, then your rigid body will turn red. If you input the IMU properties correctly, then it will turn orange and need to go through a calibration process. You will need to move the rigid body around in each axis until it turns back to the original color. At this point, you are tracking with both the optical marker data and the IMU data through a process called sensor fusion. This takes the best aspects of both the optical motion capture data and the IMU data to make a tracking solution better than both. Optionally, you may now turn down the minimum markers for your rigid body down to 1 or even 0 for difficult tracking situations. The next step that is unique to LED wall virtual production is to set up your wall and calibration board as trackable objects. This is not strictly necessary for the LED wall, but will make setup easier later and make setting the ground plane correctly unimportant. First, create a probe rigid body by rotating a probe object in the probe calibration bar while going through the creation process. The probe can be used to measure locations in the volume using the calibrated position of the metal tip. Place 4 to 6 markers on both the LED wall and the calibration board, without covering the checkered pattern or the LEDs on the wall. Use the probe to sample the corners of the LED wall and bottom left vertex of the grid of the calibration board. For the calibration board, use the Gizmo tool to orient the rigid body pivot and place the pivot in the sampled location. For the LED wall, you will need to make a simple plane geometry that is the size of your LED wall using your favorite 3D editing tool such as Blender or Maya. If you need a starting place, a sample plane comes with the Unreal Engine LiveLink plugin. If the plane does not perfectly align with the probe points, then you will need to use the Gizmo tool to align the geometry. Any changes you make to the geometry will need to be on the rigid body position and not the geometry offset. You can make these adjustments using the Builder pane, then zeroing the attached geometry offsets in the Properties pane. Next, you'll need to make sure that your eSync is configured correctly. If not already done, plug your Genlock and timecode signals into the appropriately labeled eSync input ports. Select the eSync in the Devices pane. In the Properties pane, check to see that your timecode and Genlock signals are coming in correctly at the bottom. Then, set the source to Video Genlock in, and set the input multiplier to a value of 4 if your Genlock is at 30 Hz, or 5 if your Genlock is at a rate of roughly 24 Hz. Your camera should stop tracking for a few seconds. Then the rate in the Devices pane should update if you're configured correctly. Motive is now synchronized with the other devices. Make sure to turn on streaming in Motive. Then you are all done with the Motive setup. Section 3. The next topic to cover is how to configure your project in Unreal Engine. Start Unreal Engine and choose the default project under the Film, Television, and Live Events section called In-Camera VFX. Before we get started, verify that the following plugins are enabled. OptiTrack LiveLink. Media Player plugin for your capture card, for example, Blackmagic Media Player. WMF Media Player. Camera Calibration. Open CV Lens Distortion. Media Foundation Media Player. Many of these will already be enabled. The main setup process consists of 4 general steps. Step 1. Set up the video media data. Step 2. Set up Fizz and LiveLink sources. Step 3. Track and calibrate the camera in Unreal Engine. Step 4. Set up In-Display. To set up the video media data, we will create a few media blueprints, a timecode blueprint, and a blueprint for handling your Genlock data. Right-click in the Content Browser panel, then select Media, then Media Bundle, and name the media bundle something appropriate. Double-click it to open the properties for that object. Set the media source to the Blackmagic media source. The configuration to the resolution and frame rate of the camera. And set timecode format to LTC, or linear timecode. Drag this media bundle object into the scene, and you'll see your video appear on a plane. You'll also need to create 2 other video sources doing roughly the same steps as above. Right-click in the Content Browser panel, then select Media, then Blackmagic Media Source. Open it, and then set the configuration and timecode options. Right-click in the Content Browser again, then select Media, then Media Profile. Click Configure Now, then Configure. Under Media Sources, set one of the sources to Blackmagic Media Source. Then, set the correct configuration and timecode properties. Before we set up Timecode and Genlock, it's best to have a few visual metrics visible to validate that things are working. In the viewport, click the triangle drop-down and enable Show FPS. Then hover over Stat, then Engine, then enable Timecode. This will show timecode and Genlock metrics in the 3D view. You should be aware that your timecode and Genlock is noticeably incorrect. The timecode will probably just be the current time. Once we create timecode and Genlock blueprints, these values will then be accurate. Right-click in the Content Browser panel, hover over Blueprint, and select Blackmagic Custom Timestep. Name the blueprint something like BM_Genlock. The settings for this should match what you did for the video data source properties. Click Edit in the toolbar and select Project Settings. In the search box, type in Frame Rate. It should be listed under Engine General Settings. You'll want to set the custom time step to BM_Genlock from the drop-down menu. Your Genlock pane should now be reporting accurate metrics, and the FPS should be roughly your Genlock rate. To create a timecode blueprint, right-click in the Content Browser panel. Then hover over Blueprint and select Blackmagic Timecode Provider. Name the blueprint something like BM_Timecode. The settings for this should match what you did for the video data source properties. Click Edit in the toolbar and select Project Settings. In the search box, type in Timecode. It should be listed under Engine General Settings. You will want to set the timecode provider to BM_Timecode from the drop-down menu. At this point, your timecode metrics should now look correct. The next task is to set up the Focus I Resume, or Fizz data, and our LiveLink tracking. There is a shortcut for setting up the basic Focus I Resume file and the basic lens file. In the Content Browser pane, you can click View option, located in the bottom right section of the pane, and enable Show Plugin Content. Navigate to the OptiTrack LiveLink folder, then copy the contents of this folder into your main content folder. Doing this will save you a significant amount of steps, but we will cover how to create these files manually as well. We need to make a blueprint responsible for controlling our lens data. Right-click in the Content Browser pane, then hover over LiveLink. and select Blueprint Virtual Subject. Then select the Live Link camera roll from the dropdown and click OK. Name this file something like phys_data. Open the blueprint and type Update Virtual into the search bar. This should populate two nodes, Update Virtual Subject Static Data and Update Virtual Subject Frame Data. Select each to create the two nodes on the graph. Connect the Static Data node to Event on Initialize and the Frame Data node to Event on Update. Right-click on the blue Static Data and Frame Data pins and select Split Struct Pin for each. In the Update Virtual Subject Static Data node, disable Location Supported and Rotation Support. Then, enable the Focus Distance Supported, Aperture Supported, and Focal Length Supported properties. From the My Blueprint tab, create 3 new float variables called Zoom, Iris, and Focus. Drag them into the event graph and select Git to allow those variables to be accessed in the blueprint. Connect Focus to Frame Data Focus Distance. Connect Iris to Frame Data Aperture. And connect Zoom to Frame Data Focal Length. Click Compile. Select your variables. In the Details tab, set the default value to the lens characteristics you'll be using. For our setup, the zoom is 20 mm, iris is 2.8, and the focus is 260 cm. Compile and save your phys blueprint and close the blueprint window. To create a lens file, right-click in the content browser, hover over Miscellaneous, then select Lens File. Then name the file appropriately. Double-click the lens file to open the lens file window. We will cover the calibration steps in a future section. Switch to the lens file panel. Click the focus parameter. Right-click in the graph area and choose Add Data Point. Click Input Focus and enter 10. Then enter 10 for the encoder mapping. Repeat the process of adding a data point, but enter the values of 1000 and 1000. Click the iris parameter. Right-click in the graph area and choose Add Data Point. Click Input Iris and enter 1.4, then enter 1.4 for the encoder mapping. Repeat the process of adding a data point, but with the values of 22 and 22. Both focus and iris graphs should create an elongated S-shape based on the 2 data points provided for each. Save your lens file. The process we just did is to set up the valid ranges for our lens focus and iris data. If you use a lens encoder, then this data will be controlled by the input from that device. The next step is to set up your Live Link connections. From the Live Link pane, click the plus source icon, then add virtual subject. Choose the phys_data object that we created earlier and add it. Click the plus source icon again, hover over OptiTrack source, and then click Create. Click Presets and create a new preset. Next, select Edit from the toolbar and select Project Settings. Search for Live Link and set the preset that you just created as the default Live Link preset. You may want to restart your project to verify that the Live Link pane auto-populates on startup correctly. Sometimes, you need to set this preset twice to get it to work. At this point, all of your tracking data should now be available through Live Link. The next large task is to track and calibrate the camera in Unreal Engine. From the Place Actors window, create an empty actor. Name it something like camera_parent, and move it below the NDisplay_InCam VFX_config object dropdown. Drag CineCamera Actor 1 and drop it on top of camera_parent. This will make it a child of camera_parent. Zero out the location of these actors. Select CineCamera Actor 1 from the World Outliner pane. In the Details tab, there should be a total of 2 Live Link component controllers. If you're only seeing one Live Link component controller in the Details tab, you'll need to add a new controller by using the plus Add Component button and selecting Live Link Controller from the dropdown. Name one of the controllers something like Lens and the other something like OptiTrack. For the OptiTrack Live Link controller, click the subject representation and choose the rigid body associated with your camera. For the Lens Live Link controller's Live Link tab, click the subject representation and choose the virtual camera. From the Lens Live Link controller's Roll Controller tab, select Camera Roll, then Camera Calibration. Then select the lens file you created from the Lens File Picker drop-down menu. This process allows your camera to be tracked and associates the lens data with the camera you will be using. Thus, at this point, the camera should be tracking in Unreal Engine. From the Place Actors window, create an empty actor. Name something like Checkerboard_parent. And move it below the InDisplay _InCam VFX_config object. Zero out the location of these actors. From the Place Actors window, also create a camera calibration checkerboard actor for validating our camera lens information later. Make it a child of the Checkerboard_parent actor from before. Configure the num corner row and the num corner calls. These values should be one less than the number of black and white squares on your calibration board. For us, this is 8 and 12. Also input the square side length. For us, this was 4.5 centimeters. Set the odd and even cube materials to solid colors other than just black and white for better visibility. Go to the Checkerboard_parent and click plus Add Component and select Live Link Controller. Add the checkerboard rigid body from Motive as the subject representation from the Live Link Controller tab. At this point, your checkerboard should be tracking in Unreal Engine. Double-click the Lens file from the Content Browser tab and go to the Calibration Steps tab to the Lens Information sub-tab. The transparency slider in the Viewport Settings pane can be adjusted between showing the camera image, 3D scene, or a mix of both. On the right, select your media source. Set the lens model name and serial number to relevant values. The sensor value is the trickiest portion to get correct here. This is the physical size of the image sensor on your camera in millimeters. You will need to consult the documentation for your particular camera to find this information. For the Sony FS7, the sensor is 1920 by 1080, which translates to the values of x equals 22.78 millimeters and y equals 12.817 millimeters. The next step is setting up the Lens Distortion tab properties. This will calculate the intrinsic values of the lens you are using. From the Viewport Setting pane, choose the Lens Distortion checkerboard algorithm, and choose the camera calibration checkerboard actor you created earlier from the dropdown. Show at least some of the raw camera image for this step. Place the checkerboard in the view of the camera, then click in the 2D view to take a sample of the calibration board. You will want to give the algorithm a variety of samples, mostly around the edges of the image. You will also want to get some samples of the calibration board at 2 different distances, one closer to the camera and one closer to where you'll be capturing video. Taking samples can be a bit of an art form. You will want somewhere around 15 samples from what we have found. Once you are done, click Add to Lens Distortion Calibration. With an OptiTrack system, you are looking for an RMS reprojection error of around 0.1 at the end. Slightly higher values can be acceptable as well, but will be less accurate. The next step is the Nodal Offset tab. This will calculate the extrinsics, or the position, of the camera relative to the OptiTrack rigid body. From the Nodal Offset checkerboard algorithm dropdown, select your camera calibration checkerboard actor. Take samples similar to how you did for the previous section. You will want somewhere around 5 samples from what we have found. Click Apply to Camera Parent. This will modify the position of the camera_parent actor. Set the transparency to 0.5. This will allow you to see both the direct feed from the camera and the 3D overlay at the same time. As long as your calibration is correctly set up in the 3D scene, then you can verify that the 3D object perfectly overlays on the 2D studio camera image. The last step for standard setups is to get NDisplay working. In the World Outliner pane, right-click the Edit InDisplay _In-Camera VFX _config button, and this will load the controls for configuring InDisplay. For larger setups, you'll configure a display per section of the LED wall. For this example, we will only be tracking a single display, so you can delete VP_1, 2, and 3 from the 3D view and the cluster pane. Select VP_0 and load the plain mesh we created to display the LED wall in Motive. An example file for this can be found in the Contents folder of the OptiTrack Live Link plugin. This file defines the physical dimensions of the LED wall. Select VP_0 and in the Details tab under Region, set the W and H properties to the resolution of your LED display. For us, this is 1920 by 1080. Select Node_0 from the Cluster tab, and enter the same W and H properties in the Details tab. Select the ICVFX camera actor from the Components tab. Then choose your camera object under the In-Camera VFX from the CineCamera actor dropdown in the Details tab. Compile and save. Click Export to save your NDisplay configuration file. This file is what you will be asked for in the future in an application called Switchboard, so save it somewhere easy to find. Go back to your main Unreal Engine window and click on the NDisplay object. Click plus Add Component and add a LiveLink controller. Set the subject representation to the rigid body for your LED wall in Motive and set the component to control to SM_screen_0. At this point, your LED wall should be tracked in the scene, but none of the rendering will look correct yet. To validate that this was all set up correctly, you can turn off Evaluate LiveLink for your CineCamera and move it so it is in front of the NDisplay LED wall. Make sure to re-enable Evaluate LiveLink afterwards. The next step would be to add whatever reference scene you want to use for your LED wall virtual production shoot. For this example, we just duplicated a few of the color calibrators included with the sample project, so we had some objects to visualize in the scene. If you haven't already, click File in the toolbar and click Save All. It is recommended that you should save all frequently during the whole process to make sure you don't lose any of your data. Click the double arrows above the 3D viewport and hover over Switchboard, and click Launch Switchboard Listener. This launches an application that listens for a signal from Switchboard to start your experience. Click the double arrows above the 3D viewport again and select Launch Switchboard. If this is your first time doing this, then there will be a small installer that runs in the command window. A pop-up window will appear. Click the Browse button next to the U project option and navigate to your project file. This will have a file extension of .uproject. Then click OK, and the Switchboard application will launch. In Switchboard, click Add Device, then choose NDisplay. Click Browse in the Add NDisplay Device window, and choose the NDisplay configuration file that you created previously with a file extension of .NDisplay. Click Settings from the Switchboard toolbar to verify that the correct project, directories, and NDisplay are being referenced. Click the power plug icon to connect all devices. Make sure to close your Unreal Engine project. Click the up arrow button on the keyboard to start all connected devices. At this point, everything should be running correctly. The image on the LED wall should look different when you point the camera at it, since it is calculating for the distortion and position of the lens. From the view of the camera, it should almost look like you're looking through a window where the LED wall is located. You might notice that the edge of the camera's view is a hard edge. You can fix this and expand the field of view slightly to account for small amounts of lag by going back to your Unreal Engine project into the NDisplay object. Select the ICVFX camera object in the Components tab. In the Details tab, set the field of view multiplier to a value of about 1.2 to account for any latency. Under Soft Edge, set the top and bottom and sides properties to around 0.25 to blur the edges. At this point, you are done for most LED wall virtual production setups. Section 4. From an outside perspective, the final product will look like a static image that updates based on where the camera is pointing. From the view of the cameras, it will basically look like you are looking through a window to a different world. In our example, we are just tracking a few simple objects. In real productions, you'll use high-quality 3D assets and place objects in front of the LED wall that fit with the scene behind to create a more immersive experience like seen here. With large LED walls, the walls themselves provide the natural lighting needed to make the scene look realistic. With everything set up correctly, what you can do is only limited by your budget and imagination.